Morning, students. Good morning. How was the test? Hope the test was easy. How was the test?
Yes, ma'am. Yeah, easy.
Am I audible first of all? Yeah. Was it easy?
Yes, ma'am.
Yeah, expected questions.
Yeah.
All right. Were you all able to attempt all the 5 questions?
Yes, ma'am.
Did anyone find it difficult? May I know, other than Ashwija, others? Can you tell me how did you find the questions? Can you please reply? Others, it was good. Other than Kate, Ashwija, Jane, Jason, are there any other people in this class? Sometimes others, the names which I can remember, like the ones who are interactive. Other than these, yeah, Meville, yeah, Meville, I remember Meville, Avin was, yeah. All right, fine, yeah, okay. So that's what, like, because of this online mode, uh, you should not expect a direct question as you get in VTU question papers. All right. Um, in online mode, you will be asked basic understanding how well have you understood the questions and topics and all. Okay. Based on that, the that was a question paper pattern, and still I found that some of you were not able to identify the waveform. Some have given the circuit diagram of full wave rectifier. Was the waveform given? Did it belong to full wave or half wave rectifier? Yeah, it was half wave, right? Yeah. And the waveform that was given was the output voltage that we measure across the capacitor, isn't it? And if you observe there, if you recall the waveform in the next second cycle, yes, capacitor filter, correct. Don't remember the topics. Remember how is the working of the circuit. All right. So if you observe, if you recall that second cycle, that is second half of the cycle was uh, showing zero. That is the output across the rectifier. So it was a half wave rectifier, and the waveform was of the voltage what we measure across the capacitor as a filter that was used. So some got confused and you have given full wave rectifier. So that is the thing, you have to be cautious when you are answering. All right. Okay. So we'll move on with lecture 26 today. Um, So in this class, by the end of this class, you will be able to explain the application of CMOS as an inverter, all right? And we will start module 4, that is basics of BJT, bipolar junction transistor. So you will, by the end of this class, you will be like able to know its structure, the difference between PNP and NPN transistors, the symbols, and the three regions of BJT, how it is used. All right. So I would like to start with the CMOS complementary MOSFET, which is nothing but CMOS. Um, this is something like widely used in in say digital circuit design. All right. So uh, the the microcontrollers, the microprocessors, or any digital logic circuits, what we are familiar, all right, all these use CMOS technology. all right? Say like analog circuits, which includes data converters, or if you have image sensors, or high incorporated transceivers, all such circuits include CMOS. What is CMOS? It is nothing but, as you can understand with the name there, complementary MOSFET. That means it has complementary MOSFETs included in that. All right. So basically, the structure of the MOSFET is like this. That is fabrication of the MOSFET. This is only for your information. You need not like clearly remember the things, the fabrication and all. Just understand here the fabrication part, how it is designed. All right. As you can observe, there is N-channel MOSFET and P-channel MOSFET. All right. So both are embedded together because of two different varieties of MOSFETs taken there. It is called as complementary. All right. And observe the terminals there. Observe the terminals there. The gate terminals are tied together. The drain terminals are tied together. And the source terminals are tied together. All right. So one type of MOSFET embedded in the other. All right. The complementary is embedded in the other. So this fabrication is used widely in digital circuitry design. All right. So the popular application of CMOS is nothing but used as a inverter. So in the syllabus, you have CMOS as inverter. All right. Application of CMOS as inverter. Now, can you recall? This is a typical circuit of CMOS inverter. Observe that. Can you identify the two different MOSFETs there? Can you identify the two different MOSFETs? Can you tell me which is the one used there?
That is
Can
E
it
MOSFET.
D and E? Is it D and E? Depletion and enhancement both are used.
I'm only E.
Only E. How do you identify that? How do you identify the MOSFETs used is enhancement type?
There
The
is some
diagram.
breaking of lines.
Yeah, breaking of the broken lines, right? Broken lines indicate that, yes, correct. Aiden D'Souza, correct. Broken lines indicate it is a enhancement type of MOSFET. And what else can you identify in the circuit? Absence of channel, correct. Yeah, broken lines indicates absence of channel. If the line was a solid line, we knew that it is a depletion type of MOSFET, because already the channel would be there in the beginning during the manufacturing process itself. So broken line indicates absence of channel. What else can you identify here from this circuit? It is a CMOS inverter circuit. What else can you identify? What type of MOSFETs? It's already named there. Are they both same? Both MOSFETs used are same? Are they same? E channel and N channel type, correct? Yeah. And as you can see here, Q1, the below one is your N channel MOSFET. Okay. This is identified by the direction of the arrow there. Okay. Arrow inside, facing inside is a N channel MOSFET, and arrow facing outside is a P channel MOSFET. So obviously it is an enhancement type of MOSFET, as you can see. Now observe that both the P channel MOSFET and N channel MOSFET, the gates are tied together. Okay, and it is taken as one single terminal. All right, where the input will be applied. Okay, the drain of the P channel MOSFET it is connected to VSS or VDS, main supply of 5 volts. All right. Observe the source of N channel MOSFET, that is Q1, it is grounded. All right. The excuse me. And the other terminal, what you can observe here is, which is nothing but the output V out, what you are taking, that is the output of the inverter. All right. Now, can you tell me with the circuit now, and you are already familiar with the working of enhancement type of MOSFET. What is inverter first of all? Can anyone tell me what is inverter? What is inverter? Hello, what is inverter? Inverter is nothing but a circuit which inverts the input applied to it. All right. Okay. In a simple language to remember, inverter is a circuit. Inverter enhances battery connection. I'm not getting what did that emoji indicate there. Okay. Inverter is a circuit. All right. It is a circuit which inverts the input applied to it. All right. Say, for example, if you have say inverter circuit, imagine it as a black box there. Okay. So whatever the input is applied to it, the output of that particular black box is inverted one. That is the meaning in a simple language to say. All right. So if at all you are applying, say, high voltage, if your input is a high signal, what should be the output of the inverter? If it has to invert it, the output should be low, right? Yes. Okay. If the input is high signal, the output of the inverter should be low. If at all the input is low signal, then the output of the inverter should be high, or it will be high. That is the work of the inverter. All right. Now, CMOS, the one what we are discussing now, this fabrication CMOS, it is used as an inverter. I just mentioned just now at the beginning of the class. CMOS is widely used in the digital logic circuits as inverter. So what is this inverter? Nothing but whatever you apply here, that is V in or VI, what you can see here, if you follow my mouse. So whatever is applied here, the output will be inverse of that. Now observe here, it is shown as if the input is 5 volts, okay, 5 volts, and if we take this as logic high, okay, for an instance, generally in digital system, 0 volts will be taken as logic 0 and 5 volts will be taken as logic 1. You have to remember this. All right. I'll repeat. 0 volts will be taken as logic 0 and 5 volts will be taken as logic 1. Okay. So as shown here in the circuit now and the example, if VI is 5 volts, then V0 should be or will be 0 volts. The output will be 0 volts. Okay. In the same way, if VI is 0 volts, output will be 5 volts. Correct. 5 volts. Okay. That's that as simple as that. So this is the CMOS inverter circuit. If VI is 0, output will be 5 volts. If VI is 5 volts, output will be 0 volts. Now observe the working of this, how it happens. You are already familiar now, N-channel MOSFET and P-channel MOSFET. You are already familiar. In N-channel MOSFET, we know that the majority charge carriers are electrons, right? And when a high voltage is applied to the gate, the NMOS will conduct, isn't it? Right? NMOS will be on. In a similar way, PMOS, PMOS MOSFET is nothing but where the majority charge carriers are holes here, and when a high voltage is applied to it, the PMOS will not conduct, and it will conduct only when the low voltage is applied to it, right? So that characteristics of both the MOSFETs and using in this configuration allows it to work as the inverter. Okay, so now as you can see, the gates are tied together. So when you apply, say, 0 volts or 5 volts, so one of the MOSFET will be turned on, isn't it? All right. So the output can be calculated using this, say, the voltage divider equation, as you can observe here. Okay. Say, for instance, for example, if you take VI is equal to 5 volts, what will be the output? Can you tell me which will be conducting here? When VI is 5 volts, which will conduct? Which MOSFET is on? When V in or VI is high, which MOSFET will be on? Or please don't chat, I'm not at all, okay. NMOS, correct. NMOS will be on. Okay. NMOS will be on and PMOS will be off, isn't it? So PMOS is off means the resistance offered by PMOS will be very high, and the resistance of NMOS is on means the resistance offered by NMOS MOSFET will be very low, isn't it? So observe here, applying the voltage divider rule. You know what is voltage divider rule? We are taking the output voltage across this point, all right, with respect to ground, isn't it? So R1 into Vs divided by R1 plus R2. R1 is the resistance offered by the N MOSFET, and R2 is the resistance offered by P MOSFET. Okay, using this voltage divider rule, okay, for Vi is equal to high. When Vi is high, NMOS will be on. Okay, that means R1 will be low, PMOS will be off. That means R2 will be very high. So applying that in this voltage divider rule, right? Output will be almost equal to 0 or near to 0 volts. Okay. So when NMOS is on, R1 will be very less or negligible. You can also take it as negligible. So substituting that, even though Vs is equal to 5 volts, what will be the output? Output will be equal to or approximately equal to 0 volts. Okay. So if it is 0 volts, then we know that we will take it as logic 0, right? So, sorry, 5 volts. Editor?
No, I was saying you were answer.
Okay. When V in is 5 volts, we are taking the example of Vi or V in is equal to 5 volts or high. Okay. When Vi is 5 volts, the output will be 0. In the same way, if Vi is 0 or low, can anyone explain the operation? Can anyone try the explanation of how it operates, or what would be the output? When Vi is low, when Vi is low, which MOSFET will be on?
When VI is low, P channel is
P channel MOSFET will be on. Kate, are you asking something?
Yes, ma'am.
Okay. What is your doubt?
I was answering the question that you were asking.
Answering the question. Okay, fine. Very good. Thank you. Okay. So when Vi is low, we know that P MOSFET will be on, because if you recall the working there, P channel MOSFET the channel is p-type and the gate terminal, what you apply here should be negative, right? So when Vi is low, P MOSFET will be on and N MOSFET will be off. So N MOSFET is off means R1 will be quite high, and when P MOSFET is on, R2 will be quite low or negligible. So applying again the voltage divider rule here, applying R1 Vs by R1 plus R2, substituting the R values there, the output will be approximately equal to 5 volts. All right. So using this, sorry, Jane, yeah.
Ma'am, can you increase the font size? Like, it's a bit small.
Okay, the slider. Is it okay now?
Thank you, ma'am.
Okay. All right. So taking this logic now, for say 0 volts, that is, as I said, logic will be 0, output will be VDD or say 5 volts, and that will be it is nothing but logic 1. Okay. When input is 5 volts, or in other way, it is if VDD logic is 1, for that output will be 0 volts and logic will be 0. So this is the working of inverter. This exactly is the what is that truth table of the inverter. So for truth table of the inverter is like for 0 input, 0 logic or 0 input, the output will be logic high. For 1, logic 1, the output should be logic 0. This is the truth table of inverter. All right. Do you want me to give you some time to take down this circuit and go through? If you have doubt, let us discuss. Again, you have to implement and let me. What is the question? No. The question is, Owen's question is, since Vi is 0 and V naught is 5 volts, then does CMOS produce output without any input supply? Oh, can anyone try answering this? There is I think you are able to access the chat there. Check the chat question, doubt there. Does CMOS produce output without any input supply? Is it possible? Is free energy? What do you mean by free energy, Alvin D'Souza? That's a good question, Alvin. Can anyone try answering that? Anyone? Can you try? The question is, if Vi is 0 volts, the output will be 5 volts. Then does CMOS produce output without any supply, input supply? Now observe here. Okay, observe here the working. Yes, obviously the answer is no, but justification. Can you give the justification, Revan? Can you try? What is the justification here? The answer is no, absolutely correct. But what is the justification?
Ma'am, can I try?
Sure. Yeah.
Ma'am is Ashwija.
Yeah, Ashwija, tell me. Yeah.
Ma'am, like for E MOSFETs, right? Like there must be one voltage supply so that the N channel will be created.
Hmm.
So here VI is 0, right? So there's no channel created here. So there will be no current flow.
Exactly. So, yeah, obviously, right. So this is the Vs is what we apply here. It is nothing but the biasing voltage what we apply, right? So after the biasing voltage is applied, the channel is created, and based on the gate, the potential applied at the gate terminal, whether the device is conducting or not depends, right? But again, it depends on the threshold voltage, right? So this is a VSS is nothing but the biasing voltage. And observe that it is connected to the drain terminal for P type of P channel MOSFET, right? So the biasing voltage is required there, VSS, all right? Whereas in N channel, if you recall the operation of N channel, even when VGS is equal to 0, N channel would be conducting, right? There would be current. Do you recall that? But we can make NMOS work faster by applying positive potential at the gate terminal. Recall the characteristics there. That's why when V in is high, NMOS will be on. And observe when V in is high, okay, the potential at this point and this point both are high, but the difference, the VGS will be 0 there, keeping PMOS off. Okay, you have to implement or apply all the characteristic features of both the MOSFETs here to understand the working, right? Okay. I hope that answers the question. Owen, did that answer your question? Owen, or should I repeat? Okay, yeah. Okay, fine. All right, let us move on to the next topic. If this is clear, then we'll move on to the next topic, that is bipolar junction transistors. Okay, so I guess like you already have the basics of BJTs in studied in PU, but please have patience for those who are not with basic, electronics background. I may have to give little information here. So those who have already studied, please have patience, bear with me for the repetition that is happening now. All right. Okay. So this is again the fabrication part of the bipolar junction transistors. Yeah, those who are already familiar about BJT, the basics of BJT, can you give me the answer why it is called bipolar junction transistor? Yes, it is a current control device. Correct. Exactly correct. It is a current control device. Correct. My question is, why is it called bipolar junction transistor? Those who are already familiar about BJT, can you answer that? Why is it called bipolar junction transistor? Collector and emitter, no. That is not the answer. Collector, emitter, no.
Ma'am.
Yeah. Yes, Ashwija. Bipolar junction transistor. Bipolar. What does it name
Can I
indicate?
answer?
Yes, Ashwija. Yes. Right. Yeah. Go ahead.
Ma'am, like in this type of transistor, ma'am, like in this type of transistors, like there will be like both holes and electrons as charge carriers. So they are called as bipolar junction transistors.
Correct. The current conduction in these devices, okay? The current conduction, no, it is not because of two PN junctions. No, it is not due to two PN junctions. That is not the reason, the name. It gets the name bipolar because of the current conduction. It is because of both holes and electrons, okay? because of both the charge carriers, electrons and holes, we say that there is a current or the current conduction in the device. Because of that, it gets the name bipolar junction transistor. Okay. And again, because there is two junctions, the name junction there. All right. Let us observe the working or the construction part here. So here, basically, it has a N type of material. All right. And in that, a P-type material will be sandwiched inside. All right. Or you have another type where you have a P-type material inside N-type semiconductor material will be sandwiched in between. So creating a device where you have two type of transistors here. So this is, since you have N-type, P-type and N-type, this device is called NPN transistor. And since you have P, N and P-type material here, this device or the transistor is called PNP transistor. All right. I'm repeating here. Those who already have this basics, it is repetition for you. Please bear with me. I'm going in detail for those who are not familiar with BJT at all. Okay. Now, considering this NPN transistor, okay, whatever I'm discussing here, it is applicable to PNP as well. Only the polarities will change. That I will give a brief intro later. All right. Now, as I said, you have N-type material. In between, there is a P-type material sandwich. All right. So causing three different regions here. Okay. Say, look at this. This is one region, this is one region, and this is one region. So if you have a ohmic contact to different regions here, you get three different terminals. So a transistor again is a three-terminal, right? Now, say for example, if I connect or bias, if I apply a external voltage here. So say I connect some positive potential at this point, all right, with respect to this, that means with reference to this, all right. Say this terminal will be connected to negative or say grounded, okay. That is a typical connection. You can imagine the typical connection. But let us start with the working now with connecting a positive potential at this terminal, all right. Now observe here, this is N-type material and this is N-type material. We know that the electrons are the majority carriers in N-type material, right? So when you connect a positive potential here, when you connect this terminal to positive terminal of the battery, now what happens? The electrons in N region should get attracted towards this terminal and there should be flow of electrons and eventually there should be flow of current, isn't it? But as you see, there is P-type material in between, right? So there is no path for the electrons to move freely. So because of this P-type material, there are two PN junctions, right? So here is one junction and here is one junction. And we are already now familiar that whenever there is P and N junction formed, there will be depletion region, which will be creating barrier to the flow of the charges, right? So there is no free path for the electrons to move towards this terminal, which is connected to the positive potential. Now, what can I do to remove this barrier? Say, if I apply a positive voltage at this point, a positive voltage at this point. Now, observe here, this is a P-type material. I'm applying a positive voltage at this point. All right. What is happening? I'm making this junction, this particular junction as forward biased, right? This junction will be forward biased when I apply positive potential to this terminal, and this is already with reference to say ground or say negative potential. So this junction will be forward biased. When this junction, the lower junction is forward biased, what happens? The depletion layer will vanish or disappear. Again, it depends on the voltage applied here, isn't it? Say if it is a silicon type of material, if the voltage applied here is 0.7, then the depletion region vanishes here, allowing the electrons to move inside. Okay. Now, important point to note here. This P-type material will be lightly doped. What does it mean? If the P-type material is lightly doped, means it has very less number of holes in it, which are the majority charge carriers of the P-type material. Okay. And the N-type material here, this N-type material will be highly doped, which means that the majority charge carriers here, which are electrons, the concentration of electrons here in this region will be more. All right. And in the construction part, this part of N-type material will be slightly less doped compared to this type of N-type material. So that means the electrons here will be quite slightly less compared to this. All right. So coming back to the operation, when I forward bias this junction, now electrons will get accelerated because of the positive potential here and enter into the P region. All right. They get accelerated and move towards the P region. And in the construction part, this P region will be very thin in construction, okay? Compared to the width of these two N regions, P region is very thin, very thin. So what happens when the electrons move here inside the P region? Already, because of this thin layer, they already are getting entering into this region. But remember, this is reverse bias. This junction is reverse bias because you have connected positive potential here. All right. So this junction is reverse bias. So there are two things happening here. You have two okay. Okay, there was a. Am I audible? I lost connection, I thought. Okay, okay. All right, all right. So, okay, because of this P region, which is lightly doped, less recombination happens here because there are less holes here. So the electron that enter here, the recombination will be very less. There will be a little amount of electrons that get attracted to the positive potential here. So because of which there will be small current flowing through. All right. And as I said, because this P region is very thin, all right, and the potential applied here is positive, the electrons, they get accelerated and move quickly towards this terminal. Okay, because this region is very thin and the electrons are already accelerated, they cross this reverse bias junction and get collected at this terminal. Okay, eventually saying that there is current flow happening. All right. So there are different points to note here. So when I say when we connect a positive potential here, the electrons from here are emitted, isn't it? From this region. So this region is called emitter. And where do they move? They move towards this region. Since they get collected here and to the external circuit, this region is called collector. So this is emitter region, this is collector region, and this inside center region is called base. So you have three different terminals there: emitter, base, and collector. Emitter, base, collector are the three terminals of a transistor. All right. So similarly in PNP also you have PNP. So the region here from where the holes start moving, okay, that is your emitter terminal, and inside N region, the terminal connected to that is the base terminal, and the holes that move will be getting collected at this region and eventually to the external circuit. So this region is called collector. All right. So in NPN transistor and PNP transistor, you have emitter, base, collector. So transistor is the 3-terminal device. All right. So I hope you are able to answer these first 2 questions. 2 types of BJTs are NPN BJT, that is transistor, and PNP transistor. And the 3 terminals are emitter, base, collector. Okay. Now, whenever we talk about BJTs, it is mainly used as amplifier. All right. So what is amplifier? Amplifier is a circuit or a circuit which amplifies, which magnifies the strength of the signal. Okay. Let me give you an instance. For example, if I am talking now and I'm talking to a microphone, all right? And at the receiver end, say you are at the receiver end, all right? And you are listening to what I'm speaking, okay? Generally, the strength of my speech or the auditory signal, the speech signal is very, say, weak, okay? And it won't be enough to reach you at the speaker end. All right. So that has to be magnified or strengthened, or it has to be increased in its, say, efficiency or strength. Okay. So all these things are done by the amplifier. So amplifier is the circuit which magnifies or amplifies or improves the strength of the signal. Okay, so that is mainly the application of BJT. BJT is mainly used as amplifier. All right, it amplifies the signal. Let us look at the working there. Okay, so in order to use the BJT as amplifier, we have to use BJT in active region. So actually the BJT works in 3 regions. One is active region, second is saturation region, and third is the cutoff region. All right. Cutoff region means obviously we know when the device will be in off condition. Saturation region is when the device is said to be in on condition. Okay. And if the device is used as an amplifier, then it should be working in active region. Okay. I'll discuss all these things with the circuit there. So in order to use the device, this is the typical symbol of NPN and PNP transistor here. Look at the symbol here. I would like you to note down the symbols. Okay, look at this. This is biasing circuit there. This is for NPN transistor, okay, and this is a symbol, and this is PNP transistor, and this is the symbol, okay. I will come back to this circuit after I explain the biasing part, okay, so that you will not get confused, all right. So at this point, just remember that this is a symbol for NPN. I will give you time to note down, yeah, NPN transistor, and this is PNP transistor. So biasing is nothing but how we connect external circuitry or the supply voltage in order to make the device work, okay, in order to make the device conduct. All right. So as you can observe here, the terminal which is with the arrow sign, it is the emitter terminal. this is the base, and this is the collector. All right. Now, this would be the best structure to make you understand. I'll repeat the working just now what I explained to you. All right. So if you have a emitter, base, and collector material, all right, and if you connect biasing like this, this collector terminal, see there, it is connected to the positive of the battery, all right, and P-type material where you have taken a terminal and it is connected to the positive here. So the emitter terminal, it is connected to the negative of the battery. All right. Now observe here, this junction, which we call it as emitter-base junction. Emitter-base junction, this is P-type material, this is N-type material. P-type material is connected to positive of the battery. N-type material is connected to negative of the battery. So this junction, is it forward biased or reverse biased? This junction, forward biased, isn't it? Yeah, correct. Okay. And observe this. This is again N-type material and this is P-type material and this is the junction. And this junction we call it as collector base junction or base collector junction. Either ways it is correct. Okay. This is the junction. Observe here. N-type material, the terminal here is connected to positive of the battery. P-type material is connected to negative of the battery. Then this junction, how is it biased? Is it forward biased or reverse biased? This is reverse bias, correct? Yeah, okay. If this point is clear, okay, fine, very good. If this point is clear, observe the working of the transistor. As I mentioned earlier, when you connect positive potential to this terminal, that is collector, all right? Okay, making this this junction reverse bias. So when you connect like this junction will be reverse biased, isn't it? Okay, when you connect biasing, that is some external voltage like this, then this junction will be forward bias. When this junction is forward bias and the positive potential at the collector terminal here, the majority charge carries in the N-type material, which are electrons, they get pulled towards this direction, isn't it? The majority charge carries the electrons from N region, they're getting accelerated and they're accelerated towards this terminal. And because this junction is forward bias, there is no barrier there. So easily the electrons will jump into the base region. Okay, pause here and shift to the other point. We said that this P region is very thin, okay, very thin and lightly doped. Lightly doped means the majority charge carriers, which are holes, are very less. And since they're very thin, the electrons which move inside the P region now, small amount of electrons will recombine with the holes, okay, causing a small current here. The electrons which they recombine, they get attracted to this positive terminal. So because of that, there will be small current here. Okay, so electrons, if they're moving towards this positive terminal, so how will be the direction of the current? It will be opposite, isn't it? Conventional current. All right. And if I say electrons are moving in this direction as the direction of the arrow, what will be the direction of the current here at the emitter terminal? It will be opposite, isn't it? Conventional current. Remember, the current, conventional current, what we talk, it will be always in the opposite direction of the flow of electrons. So if electrons are moving in this direction, the current at the emitter terminal will be in the opposite direction, here, in this direction. Okay, coming back here. Now, electrons have jumped into P region, and since they're already, it is a thin layer, because of this positive potential at the collector terminal, they get accelerated. The electrons get accelerated and move towards the collector. Okay, overcoming this reverse biasing condition. Okay, they are accelerated. P region is very thin. They're accelerated and they move towards the collector, causing the current to flow. Now electrons are moving this direction, means the flow of current at the collector terminal will be opposite, correct? So that is what is shown here in this picture clearly. Okay, so this is NPN transistor. The collector terminal is connected to positive of the battery. Okay, the emitter terminal is connected to negative of the battery, making this junction forward bias. This p-type material and this terminal is connected to positive. So this junction is forward bias and this junction is reverse bias. So electrons, if they're moving in this direction, the current at the emitter terminal, we call it as emitter current. Okay, and it will be in the opposite direction. When the electrons recombine with a small amount of holes here, they get attracted to this positive terminal. So because of the movement of electrons here, there will be small base current, which is shown in the opposite direction here, the small base current, all right, at the base terminal. Now electrons that are getting attracted to the collector terminal here because of this positive potential, okay, there is a current in the collector terminal, IC, which we call it as collector current, which will be in the opposite direction. All right. So when you are bias the transistor like this, when making this junction, that is emitter base junction forward bias and collector base junction reverse bias, okay, there will be emitter current, base current, and collector current in the circuit. Okay, and observe that this forward bias will be always less. The voltage that is applied here will be always less compared to VCC. Only then you will have the electrons getting attracted towards the collector terminal, and there will be say flow of current happening. Okay, I think I'm crossing the time here. I will leave you here at this stage. Okay, and I want you to go through even the working of PNP. Just analyze yourself. How is the PNP transistor working and the direction of the currents there? Okay, I will leave you at this point. So I will share this PPT, just go through this biasing part and the direction of the current. All right. So now I hope you will be able to identify the symbol there. This is a symbol of NPN transistor, which we just now I'm losing connection now and then. Okay, students, I will stop here. We'll continue in the next week. Yeah. Okay. Have a nice day.